Hello again. This is video lecture 27.1, and we are starting chapter 27, where we will be studying electric circuits. To be more specific, in this chapter, we're going to study electric circuits consisting of three types of circuit elements: resistors with some resistance R, capacitors with some capacitance C, and a source of energy, I'll say, but we're going to learn a new name for that source of energy. Generally speaking, that's a battery, or a solar cell, or a power supply, like we use in lab. But that source of energy is called, as we will learn, a source of EMF. So this video is about Chapter 27, Section 1, studying what are called single loop circuits. We're going to start with the simplest possible kind of circuit and build up from there. And so what we really have to do first, before we can even really analyze a single loop circuit, is define this newest member of the family of circuit elements. We've studied capacitors and resistors, and now we're going to study what's called a source of EMF. Please note how you say that. It's not EMF, it's just EMF. Say the letters individually. Now, here's the definition of it. It's going to seem a little bit abstract, but we'll get used to it. So this is the definition of EMF. It is the work per unit charge. Here we go again with that per unit charge concept. Work per unit charge that a device does in moving a small amount of charge dq from its low potential terminal to its high potential terminal. And I probably ought to say positive charge dq. Okay? It is work per unit charge that a device does on charge carriers that move through it. And it's a somewhat loose way of repeating what that definition just said. Okay. Doing work, remember, is a way to supply energy to a system. Okay? So that's what our source of EMF is doing. It's doing work on our charge carriers, in our current that flows through, okay? And thereby providing energy to our current. Now let's get used to the, in addition to the name, EMF, the symbol for it. And the symbol is right here, and also down here. And it's basically, I recommend you just think of it as a kind of a script or curly version of a capital E, like that. Okay? That's the symbol your book's going to use for a source of EMF. Now, by definition, EMF is work per unit charge. It's the amount of work, dW, done on an amount of charge, dQ, divided. It's dW divided by dQ. It's the work done on dQ divided by dQ. Work per unit charge. So the SI unit of EMF would be the unit of work, Newton times meter, but that's a joule, divided by the unit of charge, Coulomb. Oh, but wait. Joule per Coulomb is a combination we came across first in chapter 24, when we introduced electric potential as electric potential energy per unit charge. And in fact, a joule per Coulomb is called, the unit is called the volt. So EMF has unit of volt. Now here we have below in our drawing our first example of a single loop circuit. It's a closed circuit in which two or more circuit elements are connected by conducting wires, and that make then a closed conducting path for charge carriers to move around, i.e. so that you can have current. Okay, so this single loop circuit consists of a source of EMF. It's drawn kind of just like a box because they're not really going to say what it is. It might be a battery, like you buy in a in store, like a simple battery like you buy in store. It might be a bigger battery like you see in an automobile, or even bigger batteries that you might see in power plants. It might be a solar cell. It might be a power supply. Okay? So it's just a source of EMF, okay? An object that's going to be able to do work on positive charges. All sources of EMF have a high potential terminal and a low potential terminal. So the diagram marks those. Okay? And then they put the little curly E beside it to say it's the source of EMF. And then what your book does is draw this interesting little red arrow with an open circle at one end and an arrowhead at the other. And they do that you draw that arrow to show the direction positive charges must move through the device for positive work to be done on those charges and thereby to have them gain energy. So as long as you have conventional current, positive charge flow, in the direction of the red arrow for any source of EMF, that EMF is doing positive work and thereby giving energy to your current. And as a result of that source of EMF and the conducting wires that you see, we will have conventional current, I, flowing, in essence, clockwise around this loop because of the polarity of the EMF. With the high potential terminal at the top, the current positive charges flows to the right at the top. It then goes downward through this resistor with resistance R, leftward at the bottom part, and then back through the EMF. Note, no current disappears. Current does not get used up. It's more like if this were a closed pipe filled with water that had a little pump that just continually circulated the water around. And there are no leaks anywhere. So the water doesn't get used up as it goes around, okay? Current is somewhat like that. All right. Now, let me also remind you one thing we've already learned about current. If you take any point in a circuit, like right through this resistor, and imagine a cross-sectional slice, the current through that cross-section, which is the current I in this circuit, is the rate at which charge is passing through that cross-section. And we write that as dq over dt, in which you can think about it that I have a small amount of charge dq that passes through this surface in a time dt, and the current is dq over dt. All right, now we're going to apply some energy thinking to this single loop circuit. Okay, so that's what I'm going to go to next. We'll try to keep enough of the words and the circuit diagram visible. All right, now we're going to imagine a small time interval dt. And in that amount of time, there's a certain amount of charge, dq, that passes through that cross-section I just drew in red in that resistor. And all you have to do is rearrange the expression for current, I equals dq dt, to get dq equals I times dt. So that's the amount of charge that passes through the resistor in time dt. Positive charge in the direction of the current. But we know that when current moves through a resistor, electrical energy is converted to thermal energy. That's what a resistor does. It converts electrical energy into thermal energy. I want to know how much electrical energy is converted to thermal. I'm going to think of it as electrical energy that's lost. It's lost to thermal energy. How much energy is lost, electrical energy is lost, to thermal energy in a time dt. I'll call it dE lost. Now, it's just electrical energy lost to thermal. Well, that is just from the definition of power. Power equals dE over dt, so dE is power times dt. Take the power associated with the resistor times dt. But we have a nice little formula for power associated with the resistor. Well, at least one way to write it is I squared times R. Current through the resistor squared times R. So the energy lost, electrical energy lost, is I squared R dt in a time interval dt. Then all I did is take one factor of the I from I squared, right? I squared is I times I. I took one of those factors of I and I replaced it with the definition of I, dq over dt. That's the only thing I did next. But then I can think of this factor of dt and this factor of dt as canceling. And I have this little formula for the tiny amount of energy, electrical energy lost because of the resistor. I times R times dq, where dq is the amount of charge that flowed through that cross-section in the resistor in a time dt. All right, now, because charge is not getting used up, it doesn't get lost, it doesn't just disappear, nor magically appear, and because charge can't just pile up somewhere in the circuit, because like charges repel and that won't happen, if I take another cross-section, this time through the source of EMF, and ask how much charge will pass through that cross-section in a time dt, it's still got to be the same dq as going through the resistor. In a time interval dt, the same amount of charge dq passes through the source of EMF, by which I mean through that cross-section. But in the EMF, let's assume it's such a standard battery, we have energy being converted from a chemical form to an electrical form. Okay? That's what the source of EMF is doing. It's converting a chemical to electrical. And I want to know how much electrical energy is gained because of the work of the EMF in this time interval dt. Okay? So now I want the tiny amount of energy, electrical energy gained. Well, that will be merely the work done by the source of EMF in this time interval dt, and I'm just calling that tiny amount of work dw. Okay? The source of EMF is doing work, and that's making the electrical energy increase. Then all I did was take that expression on the right, and I multiplied and divided by the dq. That certainly doesn't change anything. But then I have dw over dq, and that's the EMF amount, curly E. That's what that symbol is. So the energy gained, electrical energy gained in the time interval dt, when the charge dq moves through that cross-section, is the EMF of that source times dq. And here comes a standard physics idea. Energy cannot just appear or disappear. If electrical energy was gained somewhere in the circuit, an equal amount of energy had to be lost somewhere else. If that weren't the case, if I had, say, more energy gained, electrical energy gained, than electrical energy lost, oh my goodness, I have a source of free energy. I'm going to patent that and become the wealthiest person ever to have lived. Okay? But unfortunately, the laws of physics don't work that way. You can't just spontaneously gain energy from nothing. Okay, conservation of energy. You get the point. So, how much energy was gained in the time interval dt when the small amount of charge dq moved through the EMF and through the resistor? E dq, curly E dq, EMF, not electric field, EMF dq is the gain, and I times R dq is the loss. You can cancel out the dq's on both sides, and you get this really nice little formula. Now, it's only for this is just for this circuit we looked at, all right? For the circuit above. That single loop circuit that had one source of EMF connected by conducting wires to one resistor. That's it. The EMF value in volts is equal to the current I through the resistor times its resistance. Notice that that combination of I times R would have units of ampere times ohm, and that also, that combination, has units of volts. Okay, so if that result has to be true by conservation of energy, then let me bring the one term over, just algebra, and you get this. E plus negative IR must equal 0. And now that way of writing it leads to a very important insight that I want to show you. So I have now redrawn the circuit diagram where I have included the source of EMF, labeled with the curly E, but I have now drawn it, not the source of the EMF, not as just a kind of a box, but the actual symbol for a battery in a circuit diagram between those two terminals, A and B. And it's a longer line spaced above a shorter line. That's the circuit diagram symbol for a battery. And a battery has some amount of EMF in volts that it can produce because of the chemical reactions going on inside. And so I would draw that little weird red arrow that way, to use your book's symbol for an EMF, to say that that's the way the current, conventional current, has to flow through the EMF to have a gain of energy. Okay, so A and B are the terminals of the battery. You can think of the points there, C and D, as the ends of the two ends of the resistor. Then we just have conducting wire connecting the battery to the resistor. We've got a complete circuit. It's got a single loop, and there's conventional current I flowing clockwise. Now I'm going to take that short little formula right there, and I'm going to write down in words what it's saying for this circuit. Okay? It says this. Imagine you are what I call a circuit inspector, and that you can flow around the loop of a circuit, kind of in miniature, inspecting all of the potential gains and drops. And you start somewhere, and you go completely around the loop exactly once until you're back to where you start. So we're going to do this little thought experiment by starting. We're going to start at the point on the lower terminal of the battery labeled point A in that circuit. And we're going to do our circuit inspection trip by going around with the flow of the current clockwise. So we go first from point A to point B. But then that means we go through the EMF in the direction of the energy gain. So we'll have a potential gain from point A to point B in an amount of the EMF. Then we go through the conducting wires. As far as we're concerned, there's no potential change there until we get to this point labeled C, and we're at one end, the high potential end of the resistor. Then we go from point C to point D through the resistor. Well, so then what I have, plus, is a potential drop from C to D. So the gain is the curly E, the EMF, and the drop is negative IR. And what this equation says is that the potential gain in going from A to B, then nothing along there, then the potential drop in going from C to D, and then nothing along this lower wire, and then I'm back to where I started. So I've done one complete traversal, but that total now I know is 0. So what we've drawn from this simple little circuit is a kind of big picture important point. Important enough in the methods of circuit analysis that it's got a name, named after a person, but it's really just conservation of energy. We ought to call it the conservation of energy rule as applied to circuits. But for historical reasons, it's named Kirchhoff's loop rule. Here's what it says in words. The algebraic sum, add up pluses and minuses, of the change in potential encountered in a complete traversal of any loop of a circuit must equal 0. And it's just conservation of energy, as I said, because when you take one point in the circuit and then go around it exactly once, all the energy gains must balance all the energy losses, so the net change in energy when you get back to where you started must be 0. That's the only thing that would make any physical sense. Like I said, what if that weren't true? What if I started at a point in the circuit with a certain amount of energy, went around once to the point where I started from, and didn't have that same starting energy anymore, but maybe had more. Well, then I've got a method of just creating energy. And I'm going to patent it and become the richest person to ever have lived. No, it doesn't work that way. You don't get energy for free. Okay? So, when you start somewhere in a circuit and you go around it in a loop, it's called, exactly once, and get all the way back to where you started, there can't be any net change in energy. Now, the way that manifests itself is any electric potential gains, positive numbers in volts, and any potential drops, negative number in volts, when all added up, will be zero. And that's what Kirchhoff's loop rule, or, like we ought to call it, the conservation of energy rule for circuits, works. Let's apply it to another simple loop rule, a simple single loop circuit. For that, I need to go to Wiley+ and show you another circuit diagram for another single loop circuit, right? That's just one loop. Let's identify the circuit elements, right? So how many circuit elements in this single loop circuit? Did you say 3? One source of EMF, which is represented by a battery. 2 resistors. The top resistor has a resistance R1. I don't know what it is, but it's R1. And the resistor on the right has resistance R2. All right, this simulation allows us to mimic applying the conservation of energy rule. Because when I drag that slider that says traverse loop, we're going to start at a chosen point. Doesn't matter where you start. The simulation starts at the point labeled E in the circuit diagram, and is going to traverse, go around the loop. We're going to be loop inspectors, circuit inspectors, and we're going to keep track of the gains and the losses in potential until we get back to point E again. And we're going to go clockwise with the current. All right, and I'll write down the gains and, well, I'll talk through the gains and losses in potential as we go. Okay? All right, so when I drag this slider here that says traverse loop, we start to move. See, now we're that red dot. We're the circuit inspectors. We're moving from point E to point A. And the first thing that happens is that we go through the EMF from low potential to high. Boom! The potential jumped. You see the bar chart? It went up by 12 volts. So we've had a potential gain of 12 volts. Now we just have conducting wire. And we're at point A. Okay? So we had a gain of 12 volts. Now let's go from point A to point B. Notice that's just through a conducting wire. Notice the bar chart is not affected. No potential gain or loss in conducting wire. Technically, as you may be thinking, that's not 100% true. There will be a tiny amount of resistance in a conducting wire, so there would be a tiny amount of potential drop, but it's negligible when you've got regular resistors like this in your circuit. Okay, now we're at point B. Now as inspectors, we're going to go from B to C through the resistance R1 in the direction of the current. What's going to happen to that potential on that bar chart? Ready? It goes down, at least as long as we're in the resistor. Then it doesn't change anymore, does it? How much did it go down? I'll help you out. See where we are? We're at 12 volts. Where are we at now? 4. So that's a potential drop of 8 volts to go from A to C. Now we're going to go from C to D through resistance R2. So far, nothing. Then, okay, look at that. What's the potential read? 0 on the bar chart. What was it before R2? 4 volts. So we had a drop of 4 volts. Now I'm going from D to E just through wire. Nothing happens. And when I get back to E, I'm at the same potential, therefore the same energy that I started from. Okay? All right. So getting back to my notes, what we saw on that example is that if we just wrote down the gains and losses, we had a gain in potential of 12 volts from the battery. We had a loss in potential of 8 volts when the current went through resistor R1. we had a loss in potential of 4 volts when the current went through the resistor R2, and nothing else happened the rest of the circuit. And sure enough, that total of the pluses and minuses is 0. Now, if I put underneath this the same idea but with symbols, it would look like this. Plus curly E, a gain of curly E, the EMF from the battery. A loss of how much when you go through a resistor? Well, from the definition of resistance, R equals V over I. So V equals I times R. So that'll just be minus whatever the current I is times that amount of resistance. Well, it's R1 for that first one. Then minus, okay, for resistor R2, what's the potential drop? The current through it, same I, but the resistance is R2. And the total must equal 0. So there I've written it in symbols, which is the way we'll often be writing it when we analyze circuits. We had a gain of EMF from the battery. We had a loss of IR1 from the first resistor and a loss of IR2 from the second resistor, where those I's have to be the same. When you have a single loop circuit, like the one I showed you on the animation, or this one right here, it has to be the same current everywhere, because it's just flowing around like water in a piping system that's closed on itself. Note, by the way, although it doesn't ask me, I can deduce something about the relative sizes of those two resistances, R1 and R2. You see what I can conclude about how big R1 is compared to R2? R1, that resistance, must be twice the amount of resistance as R2. Because the potential drop across resistor 1 is twice that of resistor 2, but they have the same current. All right, so one more useful idea in this video about single loop circuits, and it's going to be about combining multiple resistors in a connection called a series connection. Now remember when we talked about capacitors, multiple capacitors in a circuit? We identified 2 important and useful ways to connect capacitors. One was called a series connection, the other was called a parallel connection. Well, we can talk about the same thing with resistors. And the first one we're going to talk about is a series connection of resistors. And I'm going to show that to you now. So here we have another circuit diagram. Again, it's single loop circuit. It consists of 3 resistors connected in a way that we would call series. There's resistor 1, and we go out of resistor 1 through conducting wire and directly into resistor 2. And then we go out of resistor 2 using conducting wire and directly into resistor 3. One after the other. R1, then R2, then R3. Series. Serial means one after the other. Okay? And then there's a source of EMF, a battery. Okay, like so. And I have now a closed loop, so I will have conventional current I flowing clockwise around this loop, and it's the same I everywhere. All right, now we're going to apply Kirchhoff's loop rule, or the conservation of energy rule. We're going to pretend to be circuit inspectors. We're going to make one loop traversal. We've got to pick a point, go around once, and come all the way back to where we started. I tend to do my traversal going with the flow in the direction of the current. So we're going to apply the loop rule to the loop that starts at point A, see it there, and traverses, well, that's written wrong, I beg your pardon, clockwise. Okay? That's clockwise as far as I can tell. Okay? All right, here we go. The first thing that we discover when we start at point A and go clockwise around the loop is we go through the EMF in the direction of that red arrow. That means it's a potential gain of curly E. Right there. And that actually can get us all the way to point B. Then we go through resistor 1 in the direction of the current. So that's a potential drop. So you'll see it's written as minus, how much of a potential drop? I times R1, where I is the current and R1 is the resistance. Don't worry about numbers now, that's the idea, I times R1. Then we go through the resistor R2 in the direction of the current. So that's a potential drop. So minus, and how much? I times R2. Then we go through resistor 3 in the direction of the current. So another minus, how much? I times R3. And then we're back to point A. So stop, and the total must equal 0. And there's the formula you get from applying the loop rule, conservation of energy. So now some points to note then about this little circuit. When a potential difference, whatever you want to call it, V, is applied across resistors connected in series, in this case, they're connected between points A and B to the terminals of this battery, the resistances have identical current I. It's the same I through all three resistors in series. And the sum of the potential differences across the resistances is equal to the applied potential difference. That just means this from this formula. E equals IR1 plus IR2 plus IR3. That's just another way to write that formula, right? And here we have the sum of the potential differences across the resistances, and that's equal to the applied potential difference from the battery. All right, here comes the next big thing. Resistances connected in series can be replaced with an equivalent resistance, Req, that has the same current I and the same total potential difference V as the actual resistances. And here's the formula for obtaining that equivalent resistance. It comes from this expression up here by acknowledging that they all have the same I, those resistors. So you can factor the I, and then you have in parentheses R1 plus R2 plus R3, and then you just take that total, R1 plus R2 plus R3, and you replace it with a single equivalent resistance, Req. And so in other words, when you have resistors in series, to get the equivalent single resistance for them, just add up the individual resistances. And then you can draw a new simplified circuit diagram with the source of EMF and its two terminals labeled A and B. And now we've replaced the three resistors with the one equivalent resistance, and we have the same current I going around clockwise, where that Req is R1 plus R2 plus R3. Now it's worth pausing here for just a minute and pointing out, do you remember how we found the equivalent capacitance when we had, say, 3 capacitors in series? I'll remind you, the rule for finding the equivalent capacitance for 3 capacitors in series, or any number of capacitors in series, is not the same rule for resistors in series, so watch out for that. In fact, the rules that we will learn are just completely reversed. That is to say, as we will see, the way you combine resistors in series by just adding up the resistances is the way you combine capacitors in parallel. And the way you combine resistors in parallel is going to be the same way you combine capacitors in series. So it can be confusing, they're reversed. But for resistors in series, the equivalent resistance is merely the sum of the individual resistances. We'll use that fact a lot in analyzing circuits. So we close with a class engagement question on Blackboard. That goes like this. We have a single loop circuit It's got a current I in that single loop circuit, and there's a kind of a gray box that represents a battery, B. And then there's a resistor with resistance R and wires that have negligible resistance. And the arrow shows the direction of the conventional current flowing in that one loop. And then we have a series of conceptual questions about this circuit. First question, in what direction should the EMF arrow for the battery B be drawn? Right? The EMF arrow points in the direction in which you'd have a potential gain. So it all boils down to, does the EMF arrow point that way inside the battery? Or does it point that way? That would be leftward, and the first way I drew it would be rightward. Which of the two is it? That's part A. Next, part B. You'll see there are 3 points just labeled in the circuit diagram for reference. The point way over here is point A, the point between the battery and the resistor is point B, and that point to the right of the resistor is labeled point C. They're just points in the circuit. We are to rank those 3 points according to the magnitude of the current there, greatest first. Next, we are to rank those 3 points according to the electric potential there, greatest first. And then D, rank those 3 points according to the electric potential energy of the positive charge carriers at those points, greatest first. Okay? So that's what you do on Blackboard. Now, there will also be a class video in which we will apply what we've been learning about a single loop circuit for more practice. But that's all for this first video.